Inverse trig functions integration. As we have said a few times, knowing a derivative gives you an antiderivative. What I'd like to do is generalize this. Instead of the 1, put in a squared. And we get a nice little formula for the antiderivative of 1 over radical a squared minus x squared. There are two other integrals involving inverse trig functions that we will be looking at. Let's do some examples. Here's a problem that follows the inverse sine pattern. Rewrite 9 as 3 squared. And also pull out the 4. Then I have 4 times inverse sine of x over 3. Let's do another example. This example follows an inverse tan property. Now write 1 as something squared. Write 16x squared as something squared. 1 is 1 squared, and 16x squared is the quantity 4x, that whole quantity, squared. So have u be 4x, and then du equals 4 dx, and dx is equal to a fourth of du. Do your substitutions, and now you're ready to use the inverse tan rule for antiderivatives. Do the antiderivative, and then you need to substitute back. And you're all done. All right, we're going to do a problem now that involves bounds. Usually what I do is I do a substitution and I change the bounds along with everything else. In this particular case, I'm going to do just find the antiderivative while ignoring the bounds, and then I'll go back and worry about the bounds. But sometimes it's a little bit easier just to ignore the bounds, find the antiderivative, and then go back. So this one follows an inverse secant pattern. You would have in that case u equals 2x, because I need to have one quantity squared. So the 4x squared, rewrite that as 2x quantity squared. And also 25, that's 5 squared. So a equals 5. If u equals 2x, then du equals 2 dx, and dx equals a half of a du. Now, with the choice of u equals 2x, then x would be a half of a du. Do all your substitutions. Once you put in your substitutions, looks like we should do some simplifying. Let's multiply the top and the bottom by 2. And then check, do we have the inverse secant pattern? Well, we do, with a being 5. So find the antiderivative, and then substitute back. Now remember, our original problem was a definite integral. So we're going to go back to our definite integral using our result of 1/5 inverse secant of 2x over 5. So now that we've found the antiderivative, we need to evaluate. So evaluate at the top minus the evaluation at the bottom. Now simplify that. 2 times 5 over 5, that's just equal to 2. And then simplify the other quotient as well. I also got rid of the absolute values because 2 is positive and 2 over radical 3 is positive. Now before you do anything else, what you want to do is go back to thinking about what these values might be. Let's look at inverse secant of 2, and then we'll look at inverse secant of 2 over radical 3. So inverse secant of 2. If theta equals inverse secant of 2, then secant of theta would have to be 2. Take the reciprocal of both sides. The reciprocal of secant is cosine. And so cosine of theta equals a half. And the place where cosine of theta equals a half is where theta equals pi over 3. Now let's do the inverse secant of 2 over radical 3. Let's do the same thing. So if theta equals that inverse secant, then the secant of theta equals 2 over radical 3. Take the reciprocal of both sides, and we're looking for an angle whose cosine is radical 3 over 2, and that occurs when theta is equal to pi over 6. All right, so inverse secant of 2 is pi over 3, inverse secant of 2 over radical 3 is pi over 6, and then simplify. Take care, have a great day.